This morning, we're going to transition into our last unit, Unit 5. I do want to, since we've got this problem on the board still, I want to comment on this. It wasn't until this summer teaching OCHEM 2 that I finally made the connection of why learning the imines and enamine reactions is so useful before learning the carboxylic acid derivative reactions. And it's for exactly this reason. In section 19, we learned about forming imines and hydrolyzing imines down to their precursor carbonyls. And then we saw that same process show up as part of intermediates in the Grignard and subsequent acid workup of nitriles. So what I would encourage you guys to do is stay observant. Try to find those connections, because you'll always continue to make new connections. I just made that new connection. And to be quite honest, I don't think any textbook will ever tell you, by the way, we're going to introduce you to this reaction first, because in the next chapter, we're going to see it again. That's more of my job. I'm supposed to make that clear. It only just became more relevant to me today. Or this summer, rather. Okay. So we're moving into Unit 5. We're focusing in these last 2 weeks. 2 weeks. On carbonyl alpha reactivity. Now, if we happen to move through this quickly, then we might glance a little bit at amines as well. We've seen amines, but there's a lot to amines. And so if we get the time, we'll look at different things that happen with amines when you try to react with them. We're going to look at these two main types of reactions. What happens at their alpha carbon is actually governing the whole unit, but they call it alpha carbon substitutions, and then we also have these addition reactions as well. There are some new functional groups that I want us to be aware of that will be coming up in this unit. This first one is considered an enol. This is just a generic example. I suppose I could make it more generic by just putting R groups everywhere. But this is an enol, and you can see why, correct? The enol is an alcohol attached to an alkene. We're going to talk about the relationship that the enol has with our carbonyls. Enols are structural isomers of carbonyls, and they can be chemically interconverted. This is a beta hydroxycarbonyl. I'm going to put Y attached. Do you know what? I'm sorry, this might look a little awkward. I'm going to put Y attached next to the enol as well. The Y that I'm using here in place of R, I'm trying to indicate to you that this could be an ester, this could be an aldehyde, this could be a ketone. I want to say in our last unit, I gave you something similar when we looked at generic functional groups. The reason I'm not putting R is because I don't want you to think that it can't be an ester. Usually to be an ester, we don't say R, we'd say OR. I don't want to put in X either because I don't want you to think it's a halogen. So Y is kind of one of those unused variables. Now if this was an aldehyde, if Y was H, then this is a beta hydroxy aldehyde. If Y is a carbon group, this is a beta hydroxy ketone. And if Y is an OR group, this is a beta hydroxy ester. And do you see why we call it beta hydroxy? Hydroxy implies the alcohol, which means that this must be the beta carbon. Do you guys remember us calling it that, the beta carbon? And what did we call this? The alpha carbon. Then how do we refer to this? Carbonyl carbon, exactly. Which is why we've got that, carbonyl.
Wouldn't that also be a beta carbon though?
I'm sorry?
Would that also be a beta carbon or no?
It's not a beta carbon, no. Alpha is actually named respective to the carbonyl. So at your carbonyl carbon, anything adjacent to the carbonyl is alpha. So I'll try to make this clear. Esters and aldehydes only have one alpha carbon. Because an aldehyde has a hydrogen here, no carbon on the right. An ester has an OR here, no carbon on the right. Ketones are the only ones that have the potential for, not the potential, ketones are the only ones that do have two alpha carbons, alpha on the left, alpha on the right. And then also beta on the left, beta on the right. Okay, our next new functional group, this is the alpha beta unsaturated carbonyl. But this can also be called a conjugated carbonyl. Which do you guys like better? Conjugated. You like conjugated carbonyl? How come? That's funny because I think alpha beta unsaturated carbonyl is much more descriptive and self-explanatory than conjugated carbonyl. Conjugated, you have to know your vocab. Do you know what conjugated means? Could you go to a Gen Chem student and explain to them the concept of conjugation? Could you give them an example? Well, now you could. So, Raf, if conjugated carbonyl is self-explanatory, what does conjugate mean? What does conjugated mean?
It's when the bonds are not there exactly, like that they're being shared, and you can find it by seeing a double bond, single bond, and then a charge, or a free radical, or a double bond. And in this case, it's a double bond.
Okay, good. And you're exactly right. When something is conjugated, the pi bonds are not exactly where we're showing them to be with bond line structure. This is why I don't like bond line being the only way that structures are taught. This is why I truly believe MO theory has to be taught in order for you to understand it. MO theory is the one that says the p orbitals on each of those four atoms are all overlapping with each other. They're all conjugated to each other. In this way, conjugated just means related to. Kind of the same way conjugate base and conjugate acid mean related to the compound that came before them.
But in this case, you can't have a charge or anything in one of those carbons, right? It has to be a double bond.
Well, that's correct. So Rolf made the point that if you had a positive or negative charge or a free radical that was adjacent to a pi bond, this 3-atom system is conjugated. But if you have a double bond, everything is still conjugated. There's still an uninterrupted series of p orbitals. If we go back to one of our earlier chapters and we talk about groups like this, the oxygen is conjugated to the ring and the carbonyl is conjugated to the ring. And we can actually show that by showing resonance forms that show how all of them are able to interact with each other through resonance. That's conjugation. Connection of pi electrons across a system of atoms. All right, well, in my opinion, alpha-beta unsaturated carbonyl is super clear. I guess you do have to remember what unsaturated means. Can you guys give me any other example of the use of the word unsaturated?
Fat.
Sorry?
Fat.
Fats.
Triglycerides.
Mm-hmm. A lot of unsaturated fats have double bonds. They have alkenes in them. And that's what we're talking about, that degree of unsaturation. It's a little funny because by definition, a carbonyl is also unsaturated. It also has a pi bond. So we're not saying it's an unsaturated carbonyl because that's what a carbonyl is. It's alpha-beta unsaturated. The alkene is between alpha and beta carbons. Okay? A couple of other functional groups I still want to lay out. This is a beta keto carbonyl. Although, to be fair, that really just depends on what this R group is. So, with some R groups, this may not actually make the second carbonyl a ketone. So we could maybe call it beta oxocarbonyl. Why would I put in that term oxo?
Yeah.
What does oxo mean? What do we use oxo for? As substituents inside of a longer chain that has a higher priority functional group. So we're just saying that there is a carbonyl carbon at a beta position to this other carbonyl. This would be our carbonyl of reference, and at the beta position, there's another carbonyl. And one of the most common examples of a beta keto carbonyl or a beta oxocarbonyl, one of the most common examples I'll put in this green color is actually a beta keto ester. So that's where Y is equal to OR. Now, I don't want you to think that the only time you can make a beta keto ester, or sorry, a beta keto carbonyl is if one of the carbonyl groups is an ester, but it is very common. Even up here, we could have conjugated aldehyde, a conjugated ketone, a conjugated ester. This could be a beta aldehyde aldehyde, a beta keto aldehyde, a beta keto ketone, a beta aldehyde carbonyl, beta aldehyde ester, beta keto ester. There's a lot of different combinations that you can have, and there's a lot of different combinations that we'll see. Okay? Now, the last functional group is not so much a functional group as much as it is the conjugate base of a functional group. This is our enolate. You can see that the enolate is simply the conjugate base of the enol. Raf, what do we know to be true about the enolate?
Then it can switch to a different, like the double bond can also go.
It's conjugated. Because I have that three-bodied system with a negative charge, what I see is that that negative charge is delocalized. These are two resonance forms of the same compound, the same structure.
Is that also called enolate?
True. To be fair, enolate describes better the structure on the left because it is the enol that has been deprotonated, so the enolate, kind of like a carboxylic acid becomes deprotonated to form a carboxylate. The structure on the right you might refer to more as a deprotonated alpha carbon. So this gets us into one of our first topics, which is tautomerization. Which of course is just the chemical conversion between tautomers, but now we need to describe what tautomers are. Tautomers are structural isomers, but not all structural isomers are tautomers. Tautomers are structural isomers that can be chemically interconverted. So tautomerization is just the process of taking one structural isomer and making another structural isomer. Is this form of the enolate a tautomer to this form of the enolate? No.
No. Because it's all shared. It's not one or the other.
It's not one or the other. An enolate is both.
They're not structural isomers.
These are not structural isomers, yep. Those are resonance forms of each other. Enolates are not tautomer isomers. But what are? Enols and carbonyls, which I don't have like a normal carbonyl here. But you can actually see that by looking at this form of the enolate and this form of the enolate. This looks exactly like an enol that's been deprotonated. And this looks exactly like a carbonyl whose alpha carbon has been deprotonated. So the tautomers that we are referencing here are carbonyls to enols. Notice that that is not resonance arrows, that is equilibrium arrows. And once again, I'm going to put Y at one of these edges so that we can say Y can be hydrogen Y can be an R group, or Y can be an OR group. We're going to be looking at enolates and tautomers for aldehydes, ketones, and esters. We're not going to be looking at them for carboxylic acids. Do you guys have any questions on these new functional groups that we'll be exploring in these last 2 weeks? We'll be exploring their reactivity and we'll be exploring their synthesis. Okay. All right, well, I want to look at two things with you guys. First, acid catalyzed tautomerization. And I actually want to give the example that we have seen before in OChem 1 and as a review in this semester. Oops. How does this involve tautomerization? Well, the first step, the alkyne reacting with sulfuric acid, mercury sulfate, and water, it gives us this intermediate in the presence of sulfuric acid, which I'm going to write out as this. Although if you don't want it to look that cumbersome, you could just put H+. Let's think about what needs to happen in order to get this enol that forms to look like this ketone. A CH2 needs to become a CH3, and OH needs to become a CO double bond. So, the alkene carbon must be acting as a base to deprotonate my acid. Which carbon would act as the base? It's almost always the less substituted carbon that holds a more negative charge. But if this acts as a base, it's going to leave a carbocation behind, which doesn't need to happen. The oxygen instead shares a lone pair at the same time. You can argue that these can happen separately because then you just form two resonance structures, but one of them is a preferred resonance structure and one of them is not. The alkene deprotonates the acid, the oxygen forms a protonated carbonyl. The conjugate base deprotonates the carbonyl, and you're left with your carbonyl. Enol to carbonyl. All right, now I want you guys to show me the mechanism to take acetaldehyde in acidic conditions and give me ethylene alcohol. If you don't want to use H+, put some other acid in there. You can put H3O+, you can put ACOH, TSOH, but show me the mechanism for how this aldehyde gets converted into its enol form. Notice, this is just the reverse of what we've put on the board. Good first step. Good first step, bro. Good arrow. Where's this arrow starting from? Yes, love that. Yes, and now you see why it's a little confusing that H plus is the acid, because the conjugate base is nothing. But if there were a conjugate base, and there always is, it's bonding to that H, which is allowing this to form to kick back off. Yes, that's right. Perfect. Good first step. Now figure out what else needs to change in the process. Looks like you've added a carbon, but you haven't shown any arrows yet. So think about being in acidic conditions. What needs to be protonated? No. You have a CH3 here, which means you still have a CH3 here. You have a full octet at your oxygen, but now you're taking electrons away from it. So you're breaking an octet at this carbon, and you're breaking the octet here as well. Well, in acidic conditions, yeah, it doesn't make any sense to create negative charges. But if you want to do that protonation, just do it straight away. Think about, look at the mechanism that's on the board. You're going backwards. So you want to go from a carbonyl to a protonated carbonyl. How do you get there? There you go, protonate the carbonyl. Or the oxygen, protonate the carbonyl oxygen. Okay, now you're at this step. What came before that? So remember, if this is protonation and formation of the carbonyl, then the reverse would be deprotonation, elimination of the carbonyl. So we got to figure out a way to show deprotonation, elimination of the carbonyl. So you've got an arrow here that just says oxygen takes its electrons back. And then it's got an H, although you never show it bonding to an H. What we want to do is take the carbonyl and bring it down to be a protonated carbonyl. So you're going to have to show arrows that have it involve a reaction with an acid. If the last step was deprotonation, the first step of the reverse reaction is protonation. Okay, this is correct, but this is still flowing the wrong way. Once again, oxygen has a full octet, and now you're taking electrons away from it. Oxygen needs to become stable. Well, actually, tell me this. How many lone pairs on oxygen?
I don't know where you get the electrons.
How many lone pairs here? How many lone pairs here?
2.
And then here?
1.
Correct. And then here?
1.
Mm-mm.
No, 2.
Right, so how does it get a second lone pair in this step? It needs to take the pi electrons with it. Or, Roth, think about this. You need to reverse this step. In the forward direction, a lone pair is coming from oxygen to form the carbonyl. So in the reverse step, the pi bond goes to the oxygen. And a hydrogen is lost from the alpha carbon. No, not the alpha carbon. Yep. Good. Do you notice what that carbon is?
Beta
Mm-mm.
carbon?
There's
the
no-
alpha carbon.
There's no beta carbon in this molecule.
Okay. The alpha carbon and then carbonyl carbon.
That's right. And so you were trying to deprotonate the aldehyde itself, which is not acidic. Yes. No. No, because you want the OH. Just those two arrows.
I think I
Yes and no. You're not going to have these two steps here.
understand.
It's
One
just,
step.
yeah, so like this bond forms the alkene and the pi bond breaks at the same time. Two arrows, one step.
You need like an acid there, like you were saying, or can the hydrogen just go ahead and do that?
Okay, so I'll show you guys the rest of the mechanism up here. We need to take this CH3 to a CH2. That means one of the alpha hydrogens must be eliminated. What is going to do the elimination? What will do the deprotonation? Well, I chose H+, so the conjugate base is emptiness, nothing. If you chose H3O+, then H2O takes this hydrogen. If you chose sulfuric acid, then HSO4- takes this hydrogen. If you chose acetic acid, ACOH, then ACO- takes this hydrogen. Some base is going to take this hydrogen, but I don't have a base to show, so I just show the CH bond breaking to form an alkene, and the oxygen taking the pi bond back. Remember, when a bond breaks, it breaks to the more electronegative atom. So when the CO double bond breaks, it needs to break to the oxygen. So I have removed a hydrogen, formed an alkene, and created my alcohol. It's not a hard mechanism, right? But if you don't understand it, you're just memorizing stuff. But is it impossible to understand it? No, it's actually quite logical. It does make sense.
So if you were to do H2O instead of the H+, you don't put H3O+, you put H2O in there.
No, what I wanted to say was, instead of H+, if I used H3O+,
Right.
then I wouldn't attack H+, I would attack
H3O+.
H3O+, and my base would actually be H2O.
So basically it takes it away and then it goes back and it gets the other hydrogen.
Correct.
No,
That's why it's acid catalyzed.
Visually, like, seeing with water is a lot easier for some reason.
I understand. I get it.
Yeah,
I
now
do-
see what it's doing.
I do want to give you guys both options to see what H+ looks like
Right.
and what something else looks like, so I completely understand.
That makes sense.
Okay, so you learned about acid catalyzed tautomerization in OChem 1 when you learned the alkyne hydration reaction. You just didn't know that you learned acid catalyzed tautomerization. Some people do. Some professors require it to be taught. Next, we look at base catalyzed tautomerization. And guess what? You learned this in OChem 1 as well. In our hydroboration oxidation. And just remember that with alkynes, it's far less common to use borane, BH3. But we're not going to show the mechanism with borane. We're actually just going to skip down to the enol intermediate that forms. Same starting material in oxymercuration gave us a ketone. Same starting material in hydroboration oxidation gives us an aldehyde. So that's just a review of what we already knew, the regiochemistry of our alkyne hydrations. Yes, sir?
So you said, what is it?
Tautomerization. Yep.
Is creating one structural isomer from another one?
That's right.
But what does the ketone have to do with, where's the oxygen coming from? How is it a structural isomer from?
This forms, this is an enol, but this is isolated. These are tautomers.
Oh, so it's not the starting process, the starting and the ending? It's middle?
That's right. So when you run this reaction, hydration of an alkyne, you don't make a ketone right away. What's happening in the reaction flask is an enol forms in the presence of acid. And then that enol tautomerizes to a ketone.
You said you cannot isolate that enol, right?
You can't isolate the enol there. Now, I'm going to get to this, but there's an equilibrium between all enols and carbonyls. There's an equilibrium between tautomers. But for most tautomer relationships, that equilibrium lies heavily towards the carbonyl. In this reaction, once again, I'm going to skip over some of the more the beginning stuff of the reaction, and I'm going to show that this simply forms an enol. Just notice that it's an enol at a different place in the molecule. This is a less substituted enol versus previously we had a more substituted enol. And now this enol that forms in that second step, this is in the presence of hydroxide. In acidic conditions, what is the first thing you should do? Protonate something. Put a positive charge on your substrate. Look for the most basic atom, protonate it. In basic conditions, or nucleophilic conditions, what should you do? If there's something acidic, you should deprotonate it. What if there's nothing acidic? Then attack somewhere that is electrophilic. So this is a challenging thing. Acidic conditions, you can almost always predict your first step, protonation. Basic nucleophilic conditions, you have to gauge whether there is something acidic that can be deprotonated or whether there is something electrophilic that can be attacked. What do you say here? Is there anything electrophilic or is there anything acidic? What if I give you this? OH, acidic? Definitely. Anything electrophilic? Well, alkenes can be electrophilic, but if I attacked here, I'd be pumping a negative charge onto a carbon. And how often do carbons take negative charges? Not very often. So hydroxide here deprotonates the enol, which leaves me with what? It does leave me with water. The enolate. It also leaves me with the enolate, exactly. Now, enolates are always in resonance. Okay, I do want you to notice I'm just changing the conformation of my CO bond. That's because it's just easier for me to draw the aldehyde more like this. What arrows do I need to show to relate these two forms to each other?
Electrons, I want to leave.
Which way?
Where it is to it's not.
The negative, like you have an arrow going from the negative to the bond, and then the double bond going towards the carbon.
Good. Oxygen uses its lone pair to form a pi bond. Pi bond breaks to carbon. Or in other words, the pi bond moves from where it is to where it isn't. I'm going to take a second and redraw H2O as HOH, because remember, this is a base catalyzed reaction. And now this new resonance form deprotonates my conjugate acid and gives me my final product, plus hydroxide. Since hydroxide reforms, hydroxide acted as a catalyst. Similar to up here with how sulfuric acid reformed, acted as a catalyst. Okay, to be fair, I do not have to show both resonance forms. And I never have to show all resonance forms, unless you're being graded on it and you're instructed show all resonance forms. The resonance forms that I think are more valuable, you know, there's a resonance form here that puts the positive charge on the carbon. That's not a valuable resonance form to me, because it shows a broken octet when there doesn't need to be. I could technically show a resonance form here that puts a positive charge on O and a negative charge on carbon. That is really not a useful resonance form because it maximizes charges. So maximize charge, minimum octets, those aren't valuable. But here, the only distinction is charge placement. And I actually want to take a second to evaluate the stability versus the reactivity of these two resonance forms. Which of these resonance forms is a more major contributor to the enolate? Why?
Because the negative charge is on the more electronegative.
Good. Appropriate charge placement. More negative charge, a more negative atom, more electronegative atom. This is our major contributor, which is another way of saying that this is the most stable form. This would be our minor contributor, but a better way of saying that is this is the most reactive form. So when an enolate forms, it is the alpha carbon that's most likely to do something with the lone pair. All right, guys, I want to have you test yourselves again. Show the mechanism for this enolization in base catalyzed conditions. basic conditions. So what's the first thing to happen? Mm-hmm.
I think I got it.
Yes.
And then the final.
There is a resonance form here. So if you want to, maybe show me what that other resonance form looks like. On a question where you are graded, I will give you those bullet points that say show all resonance forms. So it will be more clear to you. This was a little ambiguous. And Ralph, what you did was not wrong. That was a 100% accurate mechanism. It just didn't include the additional resonance form. This is H bonded to OH minus, because I'm pretty sure H2O is neutral. And since we have OH minus and H2O, we won't see H2O act as an acid. Instead, we'll see OH minus act as a base. Notice in the last mechanism, OH minus acted as a base, and then at the end, it acted as an acid and reformed OH minus. We just want to go in the reverse now. We want to use OH minus as a base alpha carbon, and then we'll work it back to form the enol. There you go. Now, you might notice your resonance forms kind of like go from the more stable to the more reactive, and then back to the more stable to react.
Okay.
If you wanted to, you could skip this arrow, show this resonance form first, basically just flip these two,
Yeah.
and then have this resonance. Anything wrong with this? Not at all. It's 100% accurate, just a little, just a few
Just a
extra
little
arrows.
extra,
That's
okay.
all it is. Yep. No, in fact, you've got the same thing as her, which is you could just stop here, forget this arrow up here, show this resonance form first, have it convert into this resonance form, and then have this resonance form react. Actually, the only thing that is wrong is that you used OH minus, but you made H3O plus without the plus, which doesn't exist. That needs to be H2O, which then forms OH minus. Again, it reforms catalytic base. Hydroxide is the base. It's going to form water and then react to form acid again. Or water. Hydroxide. Yeah, good. Base needs to bond to the hydrogen.
It does, but then they get a positive charge here.
It doesn't.
Does it go down here?
No, you've got, these arrows are correct,
Okay.
but your base is the one that's driving that. This is what you form.
Okay.
Now you don't have both resonance forms though.
Yeah, that.
That's correct. And then this has a resonance form. And there's one last step before you get to your product. There's some things logistically that don't make sense here. You've got an arrow that starts as an atom, but these are electron arrows, and atoms are electrons. We're not going to start with H2O. H2O there is really acting more like a solvent to mediate hydroxide. So what I want you to do is just show hydroxide here, next to your carbon. And then just like I did, I want you to draw that methyl group that comes off the side of the carbonyl and show a hydrogen that comes off of it. Now that hydrogen is the acidic hydrogen. Hydroxide is the base. So from hydroxide, the lone pair points towards that hydrogen. Where's the most acidic thing here? Okay, well let's be fair. Hydroxide being basic or nucleophilic conditions, if there's nothing acidic, it might do an a nucleophilic attack to an electrophile. And there is an electrophile. I gave you guys the mechanisms in the aldehyde and ketones reactions for hydration. That hydroxide can attack a carbonyl carbon and do acyl addition. We even saw that with esters. Hydroxide can attack the ester carbonyl and do hydrolysis. So there's competition here between hydroxide acting as a nucleophile and doing acyl addition and hydroxide acting as a base. But given that we know the product we want to see, that's the mechanism we're showing. Hydroxide goes for the most acidic position. That's the alpha hydrogen. That means that the CH bond breaks to the carbon. I'm going to show the CH bond only breaking that far so that I can show both resonance forms. Carbon holds the negative charge, and through resonance, oxygen holds the negative charge. Plus, hydroxide deprotonated a hydrogen. I make water. But water is not the end step here because my my enolate deprotonates water to give me my final product, which is my enol regenerating hydroxide. John, I don't understand. Right on the board, you said when the when the alpha carbon holds the negative charge, that's the most reactive. Why then am I showing the most stable resonance form reacting with the acid?
Conjugated?
Yeah, but the negative charge sits both on carbon and oxygen. And when the negative charge is at oxygen, it's less reactive. When the negative charge is at carbon, it's more reactive. Wouldn't the carbon react?
I mean, if the carbon just reacted, we just go right back to our starting product.
Correct.
So,
We just go backwards. So am I saying that this has to happen? No. What I'm saying is that this is driven by equilibrium. And it's driven more towards the carbonyls for this exact reason. If this enolate forms, it's more likely to react from the alpha carbon and just form the carbonyl. If an enol forms, oxygen is far more acidic than a comparative carbon-hydrogen bond. So if we look at pKa's here, the pKa of this OH is going to be less than 15. And the reason it's less than 15 is because normal alcohols have a pKa around 15. Phenol, which is conjugated with the aromatic ring, has a pKa around 10. This alcohol is conjugated to an alkene, but not conjugated to an aromatic ring. So its pKa is going to lie somewhere between 10 and 15. But this CH, its pKa is going to lie higher than 20. It's going to be less than the normal CH pKa value. This is more acidic than normal CH bonds. But its acidity is still weaker than the acidity of the OH. So if you have an enol, it's likely to act as an acid. If you have a carbonyl, it's less likely to act as an acid. So the equilibrium between the two lies heavily towards the carbonyl. You get very little of the enol. We're showing this reaction. I want to take a ketone and make its enol form. That doesn't mean I take 100% of the molecules of the carbonyl and turn 100% of them into the enol. Maybe I turn 5% of the molecules into enol. Maybe 10%. Equilibrium does not have to be all or nothing. In fact, it rarely is. It's usually rides somewhere between the two of them. Okay, I want to give you guys a break. I want you to get up, get your blood flowing, move around. Because when we come back, we're going to talk more about acidity. Alright, you know what? I want to do actually a little bit of practice with you guys. On these compounds, tell me how many alpha hydrogens are present.
And which one?
All three of the compounds, how many alpha hydrogens are present?
First one, 0.
Just give everyone a second to work on them. Keep up the good work though. And then for the second set, I want you guys to look at what is the tautomer form. I'm going to give you the carbonyl and have you predict the tautomer, and then I'm going to give you the enol, have you predict the tautomer.
We'll go to the most secure side for the double bond.
We'll talk about that, but you're talking about this, Caesar?
Yeah.
There's only one option for all of these compounds. Well, they all have alpha carbons.
I mean hydrogen.
Correct. Doesn't have any alpha hydrogens. Good.
And the bottom one would put in the final product, or what was the bottom?
The tautomer form again.
Not the last one?
I don't know if you're done with it yet or not. Oh, I misunderstood that as OH. I apologize. No, that one is correct. assuming you meant put a number here, but you just kind of saw that number and thought it was there. Yeah.
Yeah.
Good, 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 great, good. Did you put your numbers up for questions? Great, awesome. It's clicking, huh? You guys are, oh, I think you
I didn't draw it right on my thing.
got a carbon chain.
Yeah. I just decided I was done drawing. There you go.
This one's correct. These two are not. This is off to a good start. You know it's going to have OH. Same here. This one's actually correct. But this one is missing a lot. Yeah. Okay. I'm going to start putting up some answers. How many alpha carbons on this ester? Just one. It would be the carbon of the benzene ring. And the carbon of the benzene ring doesn't have any hydrogens if it's substituted. So this has 0 alpha hydrogens. Just to be clear, that means that this compound has no tautomer form. It doesn't have an enol tautomer. Notice in our mechanisms that all the tautomerization takes an alpha hydrogen or gives an alpha hydrogen. So if there is no alpha hydrogen to take or give, there's no tautomer. 3 alpha hydrogens here. All 3 of those methyl alpha hydrogens, they're equivalent to each other, but that's one thing to talk about is there are 3 alpha hydrogens. And then here there is 1 alpha hydrogen. So this carbon, or this ketone had 2 alpha carbons, but only one of them had alpha hydrogens. The aldehyde, once again, it only has 1 alpha carbon. A lot of people mistake the aldehyde hydrogen as an alpha hydrogen, but the aldehyde hydrogen, by definition, is the aldehyde hydrogen. So there's just the 1 H coming off of that tertiary alpha carbon. All right. Just for clarification, if we wanted to, we could look at the tautomer forms for these two. They are both able to tautomerize into enols, but this ester cannot. And that's exactly what I saw you guys taking advantage of here. You looked for the alpha hydrogens, removed them, and created an enol. Now, with the first compound, the ester, it is a bit confusing because that's not a normal enol, that's an enetherol, right? An enol enether? I don't know how you'd name it, but it's got both groups.
Is that like any less stable than like the other forms where?
Like the enol of a ketone or the enol of an aldehyde?
Yeah, or like the fact that it's like not substituted on the other side of the.
Well, I mean, you could add a carbon chain if you wanted to. We're going to talk about stability, which has a lot to do with acidity. And so we're going to look at acidity and how that predicts stability of the enol tautomer. Yep. So when you see this enol that is also an enether, you know that you have the tautomer of an ester. I realized that in the examples I gave you guys earlier, I was only showing you tautomerization of aldehydes and ketones. But I want you guys to recognize that we're going to deal with esters a lot here too. Now the way to take an ester to its tautomer form, you can't do it in acidic conditions. You know what? This might warrant me just putting this on the board in a little bit. You cannot use acidic conditions to convert an ester to its enol. That's because acidic conditions hydrolyzes esters to carboxylic acids. Not useful. So you have to use basic conditions to tautomerize an ester. And if you use hydroxide as a base, you will also hydrolyze the ester. So the base for ester tautomerization has to match the ester linkage. We'll talk about that in a little bit. Here, I get the enol of my aldehyde. Now you could keep the carbon chain like this, although the enol is probably going to form in the lowest energy conformation, which would be trans rather than cis. And the ketone only has one alpha hydrogen position, 2 alpha hydrogens, but only one position where it can be turned into an enol. Down below, what I noticed you guys were doing good at was recognizing this is the carbonyl carbon. It's only bonded to one other carbon. That's going to become an aldehyde. Here's the carbonyl carbon. It's bonded to 2 carbons. That's going to become a ketone. Here's the carbonyl carbon. It's bonded as well to an OR group. That's going to become an ester. Okay? And here's that comment that I made before. I just really want to reiterate it. In the tautomerization of an ester, the base that is used must be an OR minus group. You cannot use H3O plus because that will hydrolyze it. You cannot use OH minus because that will hydrolyze the ester. And if you use something like OR minus prime, so I just want to really indicate this is a different carbon group. Then you can do transesterification on your ester. So the base must match the ester linkage. Let's say that R up here is methyl and R prime, for instance, OR prime minus is ethyl. This allows transesterification. So you must use a base that matches your ester linkage. All right, any questions so far? We are, more often than not in this unit, going to start with carbonyls, try to take advantage of them to form enolates, and then use the enolates in reactions. enolates are weak nucleophiles. So in order to make an enolate, to use it as a nucleophile, we need to first deprotonate that alpha hydrogen. So let's look at ranking or comparing the acidity of different alpha hydrogens. We'll look at a few factors. First, pKa increases with increasing induction. Okay, induction is kind of a bad word because it can mean both the push of electrons and the pull of electrons, but we're just going to keep it meaning the push of electrons here. If we look at the alpha hydrogen of an ester, a ketone, and an aldehyde, and I'm going to highlight the acidic hydrogen here in red. The aldehyde hydrogen pushes very little in that direction. Doesn't have a lot of electron density, but hydrogen is not very electronegative. So all of its electron density gets pulled in. A carbon group has more electron density, which means that it pushes more towards that alpha position. I want to make something clear. When we're talking about this acidity, having electron density push in means there's more negative charge at that position. It's less likely to give away its hydrogen. Because it has more negative character, it's more likely to be a base if its hydrogen is ever given away. And then there's the ester group. Now we know that the oxygen is electronegative. It's pulling electrons towards itself, but this oxygen is also actively engaged in resonance. So we can look at that as being a lot of induction. It's pushing a lot of its electron density through resonance towards that carbonyl carbon. So when we look at pKa values, we get a pKa of about 25, about 20, and about 17 for each of these positions. And again, if it doesn't make sense to you how this induction arrow is trying to explain why it's a worse acid, then we can look at it in terms of the conjugate base, and we can say, is anything happening with that negative charge? Well, yeah, this oxygen is pushing a lot of electron density that way, so that negative charge is even more reactive. Versus this hydrogen, which is not really pushing a lot of electron density, that's not very reactive. So we get the best acid and the worst base. At our aldehyde's alpha position. Okay, factor number 2, pKa decreases with increasing substitution. I want to make a point. I know that sometimes students get confused when I have these like ranking effects, and now I'm talking about the pKa going different ways. So if you wanted to, you could actually change the way that we think about point 1, which is you get more acidic, your pKa gets lower when you have less induction, less electron density being pushed in. And then the rest of them are going to keep talking about when pKa comes down. Would you guys agree that I could look at a primary alpha carbon on an ester, secondary or tertiary carbon on an ester, or I could look at primary, secondary, tertiary on a ketone, primary, secondary, tertiary on aldehyde? When I talk about substitution, this could be any of the functional groups that we've got here. I'm just going to look at one functional group. We're going to look at our aldehyde and see what happens when that aldehyde alpha hydrogen becomes more substituted. So this trend holds true for all of our functional groups. More substituted ester alpha carbon, more substituted ketone alpha carbon, more acidic. So we know the pKa of this first compound because we just had it over here. This has a pKa around 17. That's if it's a primary alpha carbon on an aldehyde. If we substitute it to be secondary, the pKa drops by an order of magnitude, 10 times more acidic. And if it's tertiary, 2 orders of magnitude, 100 times more acidic than the primary carbon. You know what? I want to show you guys as well the conjugate base that forms there, because the conjugate base can help you understand why it's a better acid. What do you see changing in those conjugate bases? What do you see? What's the difference?
It's like a more stable alkene.
Mm-hmm. More substituted alkenes are more stable. So once again, we have our best acid and our worst base. The most stable base is the most substituted alkene. Remember, we learned this in OChem 1. A more stable alkene is a more substituted alkene. This is Zaitse's rule. You form the most stable alkene. So when given the choice, and this only happens on ketones, when given the choice, you go towards the more substituted alpha carbon because that's going to give you a more stable alkene because it's more acidic. One way that I like to think about this is actually kind of induction again. This has a resonance form where the alpha carbon is holding the negative charge, and that primary carbon can hold a negative charge well. There's not a lot of electron density repelling it. A secondary carbon cannot hold a negative charge very well. There's a lot more electron density causing it strain. A tertiary carbon is terrible at holding a negative charge. So these other groups are actually pushing the electron density back towards the oxygen, which is going to make it more stable. less acidic, or sorry, less basic, lower pKa. Okay, we don't have time to get into the third and final component of acidity, so this is where we'll pick up tomorrow. We'll talk about how resonance impacts acidity. We'll look at different types of bases that can be used to control our regiochemistry. And then we're going to start looking at alpha carbon substitution reactions, chapter 22, or section 22. And then we're going to look at condensation reactions, addition and condensation reactions, section 23. So tomorrow we'll get into most of section 22. Next week we'll spend on section 23. All right, guys. Take care. I'll see you tomorrow.